Okay, I can find.
Do you need like dollars?
No, I have there's a lot of problems. We should pick up this.
Yeah, I know.
Hey, Papu,
Yes.
can you drop the screen for a second? Hey.
Oh, okay.
Donate to the charity of cause over
Charitable cause.
Is it dark enough or do you want it darker, brighter?
Dark नाही मला नुसतं स्क्रीन केवढा मोठा ए बाबा तू असं नको करू.
This is sort of like the line at UIUC. These are some of the people that I've directly worked with on this project. Some of the research in my thesis has already appeared in conference papers, journal papers have been submitted and are currently under review. The problem that motivates my research arises in important applications in science and engineering, such as modeling of ocean waves, acoustics, gas dynamics, and modeling of traffic flow. These phenomena are, these applications involve. I'll start. Good afternoon and welcome to my PhD defense. My thesis is on space-time meshing for discontinuous Galerkin methods. Professor Jeff Erickson is my advisor. Professor Michael Louie is on the phone, and the rest of my community members are in the room. The research in my thesis is my contribution to a larger project at the Center for Process Simulation and Design at UIUC, and I've collaborated with several researchers at UIUC in CS, math, and theoretical and applied mechanics. Some of the research, some of the results have appeared in conference papers, journal papers have been submitted and are currently under review. The problem that motivates my research occurs in many important areas in science and engineering, such as some of the ones listed here, modeling of ocean waves, acoustics, gas dynamics, and traffic flow. These applications involve simulating wave-like phenomena, which are transient, time-dependent phenomena. And computer simulation is important, for instance, say for predicting earthquakes or for simulating machine parts, designing mechanical assemblies. And such simulations involve solving space-time hyperbolic partial differential equations. A canonical example of a partial differential equation of this form is the wave equation written here for a one-dimensional space domain. So imagine a guitar string plucked somewhere in the middle, and this sets up vibrations in the string which travel back and forth along the string like waves. In this PDE, the wave speed omega is the speed at which waves travel and could depend on the material properties of the string. An example that we were able to solve, I'm on the linear elasto dynamics slide. An example that we were able to solve with our meshes and with our general solution strategy is the following problem in linear elastodynamics. When a tensile force is applied to a rectangular plate with a crack in the center, this causes shear waves to travel back and forth through the domain to the plate. And the interesting patterns we observe are reflections in circular patterns of the waves from the tip of the crack. And on the left is a schematic picture of a schematic of the situation, the physical situation. On the right side, we have the solution that was computed using our methods, which indicates the speed at which the waves are traveling, as well as the strain energy density. The focus of my thesis is mesh generation. The space-time mesh is a partition of the space-time domain into simplices like triangles, tetrahedra, and higher dimensional analogs. Given a space-time mesh, space-time discontinuous Galerkin methods, these are the methods that we would like to support. These are finite element methods that compute the approximate numerical solution over the underlying domain, over the mesh. If you're familiar with finite element methods, you'll be familiar with this. In my thesis, I give algorithms to generate space-time meshes in d dimensions cross time. So here d denotes the dimensionality of the space domain. Like the previous example where we have a rectangular plate, d equals 2, and we solve it by constructing a three-dimensional tetrahedral mesh. The algorithms in my thesis support an efficient, parallelizable, linear time solution strategy by SDG methods. By order n, your n denotes the number of elements in the mesh. In my thesis, I proved worst case guarantees on the size and the quality of the mesh. So this is an overview and the context of what the research is about. Let me now describe the problem that I went out to solve. I'm on slide number 6 with the title causality on it.
Yes.
Okay. The phenomenon that characterizes space-time hyperbolic problems is causality, or to be specific, bounded causality. And this is a fairly intuitive notion. On the next slide, I show what this means. If you have points in space-time, we say that point A influences another point B, written as A precedes B, if and only if changing the physical parameters at A, say the amplitude of the vibration or the temperature or the pressure, could possibly change the solution at B. So this illustrates, for instance, how information travels through the space-time domain. Points influenced by A are approximated by a cone. I call this the cone of influence, which has apex A and slope equal to the reciprocal of the wave speed at A.
I have a quick question here.
Yes, please.
I know you're dealing with hyperbolic PDE, and when you have the wave equation, then omega, of course, is the wave speed.
Right.
But what if the hyperbolic PDE is not the wave equation? How do you define wave speed?
So there they fall in the same sort of canonical form, and you can extract the wave speed out of them. So we define wave speed, so hyperbolic problems generate characteristics at every point in the domain.
You define characteristics.
There are characteristic vectors, and these characteristics are given or can be found, and what we compute is the slope of the characteristics.
Mm-hmm.
And the slope gives us a local approximation to the wave speed. Okay. So a fast characteristic would correspond to a shallow cone, and a slow characteristic would correspond to a more steeper cone. So from the characteristics we can extract the wave speed, and that's the wave speed at the point A.
So wave speed is defined at individual points then?
Yes.
Okay, very good. You can continue.
Right. Thank you. If neither point A influences nor B influences A, then we say that points A and B are independent. Then this notion of influence can be extended. In the next slide, I show how it applies to larger subsets of space-time. For instance, if you have a space-time mesh, in the mesh we say that element A influences another element B, written as A less than equal to B, if and only if some point of A influences some point of B. What this means is that if A influences B, then A must be solved no later than B, otherwise the solution at B is not valid. If A influences B and B influences A, then A and B are coupled and must be solved simultaneously. In the figure I show two elements A and B, where A influences B, B influences A, and they form a coupled system of two elements. A patch I define as a set of elements that must be solved simultaneously. A patch plus its inflow information is a solvable unit as far as the SDG solver is concerned. So in this illustration, I show a patch consisting of two elements A and B. The inflow information is the solution computed everywhere in the past, but we only need local inflow information to compute the solution. The algorithms in my thesis are to generate meshes, space-time meshes, incrementally from bounding the sum over all the patches of the mesh of the time to solve each patch. So the problem can be stated as follows: generate a mesh where which is with an algorithm that is efficient under this kind of a method. I'm now going to talk about the solution to this problem. What is the algorithm that I propose in the thesis to do the mesh construction? It's an advancing front meshing algorithm. Here is the basic algorithm. Here's the basic outline of how the algorithm proceeds. We start with the initial triangulation. The input is a triangulation of the space domain at time t equals 0, given all the initial conditions. For example, again in the corrective wave scattering problem, we have say we started with a mesh of 8 triangles of this rectangular domain, and we're given the initial conditions. The output of the algorithm is a simplicial mesh, one dimension higher. In the corrective example, we constructed a tetrahedral mesh. The mesh was constructed by constructing a sequence of fronts, tau 0, which is the initial space mesh, tau 1, tau 2, and so on, which are embedded in space-time, and between successive fronts, we created patches of a few elements. A front is a terrain. In the illustration, I show a front in 1D cross time. It's the red polygonal line, which is a 1D terrain in the two-dimensional space-time domain. I will show illustrations later on about more complicated fronts. So here's an example of the working of the algorithm. Initialize the initial front with the input triangulation. And we repeat the following process: advance a local neighborhood of the current front to obtain a new front. Yes, please.
Could you go back one slide? I'm not happy with your definition. A front is a terrain.
Yes.
I could have also said a terrain is a front. Is that defining anything?
It's defining what it means geometrically. It's a time function. It's a function from the space domain to the set of time values. Another way to think of it in terms of causality is that it's a maximal set of points that are independent.
Okay, let me ask you another question. What's a terrain?
Okay. A terrain is a manifold, a surface, which has in this case, which would have a spatial projection. So spatial projection is simple and is a triangulation. So imagine a triangulation in space.
Was I supposed to already know that?
I can define it.
So this is a standard term in computational geometry.
Okay.
Probably
So you're telling me I should have already known that, right?
the, well, no.
Or
We should have already known that.
Yeah.
Maybe.
Or I should be able to define it sort of more formally.
Okay.
So there are two ways of.
So why did you introduce the word front? It's simply synonymous with terrain.
I use the term front because it's popular in the literature. People use advancing front algorithms, and I want to convey that this is in the same style. It could be. It's also a frontier of the solution and the mesh construction. So a frontier would be a valid term as well. It's mostly to point out that yes, other people have used advancing front algorithms to construct meshes.
Okay.
And we have disadvantages of those other methods.
But here do you want to imply that the front is causal, or is that a modifier?
It is a modifier to the front. So here's an illustration of the algorithm. Repeatedly advance a local neighborhood of the current front to obtain the new front. Interleave this mesh construction with calls to the DG solver to compute the solution. Each new front is obtained from the previous front by a local operation. As illustrated in these figures, we started with initial triangulation. We lifted a local neighborhood, the triangles around a vertex, up in time and created a patch of tetrahedra. After the patch was solved and accepted, the front was advanced, and then we advanced some other local neighborhood in this process repeats. The constraint that must be satisfied, this is a geometric constraint on every front, is that the front must be causal. A front is causal if and only if it is an independent set, that is, no 2 points of the front influence each other. Another way of looking at it is that for any triangle on the front, so this is a 2D cross time front, for every triangle on the front, every point on the triangle has its cone of dependence, which is symmetric to the cone of influence, separated from its cone of influence. That is, information propagates in only one direction through this front, from the past into the future. Points on the front depend only on points in the past, where the solution has already been computed, and they influence only points in the future. Geometrically, that means that the slope of this triangle must be less than the slope of the cone, which is 1 over wave speed. Temperature is the first space-time meshing algorithm with provably correct and with provable guarantees. That was proposed by Abhyankar and Schaeffer in 2000. We'll have the citation on the next page. Temperature is an incremental algorithm in the same framework. What it does is the specific neighborhood that it advances at every time is to advance a single vertex P to P prime, which creates a patch of, in this case, tetrahedra, all sharing the edge P, P prime. Because the old and new fronts are causal, the patch can be solved immediately. In 2D cross time and higher dimensions, it was pointed out that by being too greedy, that is, because temperature is trying to maximize the progress at each step, which is the height of the tentpole, by being too greedy at each step, the algorithm may get stuck because it may prevent progress in the next step. There's a trade-off between how much progress you make in the current step and how much progress you can make in the next step or subsequent steps. So Erickson and others, in a journal paper that just appeared recently, the conference paper on two progress constraints, that's in the front, and when causality and progress constraints are together in both the entire step numbers, by the same amount. So here we're looking at a local progress which is proportional to the local geometry of the frame. The contributions in my thesis are to improve temperature. So in the same framework, I extend the algorithm to solve more. The first contribution I want to talk about is how to adapt mesh resolution to error estimates in 2D cross time. What this problem means is that for required accuracy, you need to vary the element size, that is the size of the elements in different parts of the domain, depending on whether there are interesting things happening in the solution in that part of the domain or not. And so we adapt the mesh resolution to error estimates in the first result. In the second result, we adapt the duration of space-time elements to changing wave speeds in d dimensions cross time. So notice that the causality constraint depended on the wave speed, and for many problems, many interesting problems, the wave speed is not constant, and so we need to adapt the duration of these elements to the wave speed. The wave speed is fast, the duration, the height of the tentpole is going to be small, the wave speed is slow, the height of the tentpole is going to be big. The first problem by itself, so just doing mesh adaptivity in 2D cross time, is trivial in 1D cross time, for one-dimensional space domains. It's easy to show that causality is a necessary and sufficient condition on the fronts to guarantee progress. In higher dimensions, d greater than or equal to 3, this problem remains open, even for the fixed wave speed case. The second problem is non-trivial even in 1D cross time, and I will show you what is the complication that arises. And in my thesis, I give an algorithm that works in arbitrary dimensions, including d equals 1, of course. Specifically, I give an algorithm to solve nonlinear problems efficiently and adaptively. So both these results are combined into one algorithm. This requires new constraints and a new meshing algorithm, which I give in my thesis, and I prove correctness. The third result I want to talk about during this talk is initial progress on adapting size and position of mesh features to track moving boundaries. What does that mean? If you have a space domain that does not change with time, the space-time domain that it describes looks like a SUD. You have a fixed space domain cross the time axis, and you get a space-time domain whose boundary consists of vertical planar facets. When you have more interesting things happening, for instance, the space domain could be changing shape, geometry could be changing, it could be rotating, it could be shrinking, it could be growing with time. Now you have a more complicated boundary that you want to track by aligning mesh features. Without motion, whenever you advance a vertex in time, you automatically create vertical facets, vertical triangles, which line up exactly with the space-time boundary. When we have motion, the problem is more complicated. So in my thesis, I propose a set of more general front advancing operations, in addition to just pitching vertices in time vertically. And these are required and useful for boundary tracking and possibly for tracking other singular surfaces like sharp fronts. I give a framework to perform the various operations when they are possible and desirable. I would like time on that. I'll go details of the algorithms that I'm now on slide 19. I would like to illustrate where the progress constraint comes from. Remember, being too greedy is harmful in the future, and so progress constraints are required to limit the progress at each step so that progress is guaranteed in the next step. And I'd like to show an instance here. Imagine a front consisting of a single triangle PQR in space-time. On the left, I show the spatial projection of this triangle. Notice that there's an obtuse angle at R. This triangle in space-time determines a plane in space-time, which is the graph of a linear function. The gradient of this linear function is a vector in R2. The direction of this vector is the direction of steepest ascent, and the magnitude of this vector is the slope of the plane. So on the right-hand side, I show a picture of R2, the vector space R2. The point O in the middle is the origin, and I draw a disk whose radius is equal to 1 over the wave speed of triangle PQR. So take the maximum wave speed over all points of the triangle PQR and take the reciprocal of that to compute this disk. The gradient vector of triangle PQR can be denoted by an arrow in R2. So instead of drawing the entire arrow, I just draw the head of the arrow. So the gradient vector is an arrow from the origin to point number 0. Point 0 represents the current gradient of triangle PQR. Because it's inside the disk, it means that the magnitude of this gradient, the slope of this triangle, is less than the causal slope, less than 1 over omega. That means triangle PQR is causal by definition. Assume without loss of generality that P is below Q, which is below R, in order of their time coordinates. When I lift P in time, vertically in time, the gradient vector, the gradient of triangle PQR, so imagine this as a continuous process. So I'm advancing P to say P prime in some continuous process and increasing the time coordinate of P continuously. As I increase this, the gradient along QR remains unchanged. It's a linear function. Whereas its component perpendicular to QR increases in a direction pointing towards P. This is illustrated by the arrow going from point number 0 to point number 1. At point 1, P is no longer a local minimum vertex, and in fact Q is the next local minimum vertex. In this figure, I indicate the direction in which the vector changes by three directions: OP, which is perpendicular to QR, OQ, which is perpendicular to PR, and OR, which is perpendicular to PQ. So the gradient vector will always move along one of these three directions when a single vertex is advanced. On the next slide, slide number 20, I show that if we limit our progress to point number 1, then in the next step, when Q is advanced, the new local minimum is advanced, the gradient vector advances sufficiently, Q makes positive progress while still satisfying causality. However, on slide number 21, if I am too greedy in the current step and I advance all the way from 0 to 3, then you can see that in the next step, by pitching Q, I will almost immediately violate causality. And to prevent that, the progress constraint imposes a restriction not to enter the red forbidden zone. Similarly, on the other side, we have another forbidden zone, and these two red forbidden zones represent the progress constraint, which is parameterized by the wave speed 1 over omega. On slide number 23, I explained what the complication arises when the wave speed is not constant. For nonlinear PDEs, the wave speed omega is not a constant, but can be in fact solution dependent. Increasing wave speed breaks the old algorithm in one of two ways. One, if the local current wave speed is used for imposing causality, then after pitching a vortex, even by a very small amount, immediately the new triangle may have a fast wave speed, which makes the triangle immediately not causal. A way to solve this is to assume some global maximum upper bound on the wave speed everywhere in the domain and impose that at every step of the algorithm. However, that would mean that the spacetime mesh consists of many more elements than necessary, and that would be an inefficient way to solve this problem. So, because of this, because of wave speeds increasing, at every step, the current front, must satisfy a progress constraint that anticipates the wave speed in the next step. And in my thesis, I derived an invariant, which I call a progressive invariant, that guarantees progress even when wave speed increases discontinuously. So as long as each front is progressive, I can advance a local minimum vertex of the front, an arbitrary local minimum by a positive amount, and ensure that the new front is also progressive, even when the wave speed functions increasing discontinuously. I give an algorithm to greedily maximize progress subject to this progressive invariant. We make one assumption about wave speeds that allows us to do this, and this assumption is called no focusing. The definition is on slide number 24. Here is the situation. In the figure, I illustrate some front in 1D cross time, say. The solution has been computed for all the points on the front and in the past. So the actual wave speed is no 2 points Q and Q prime, and their cones of influence have been computed. Now imagine a point P in the future where the solution has not yet been computed. The no focusing assumption gives us an upper bound on the actual wave speed at P. So it allows us to conservatively estimate the actual wave speed at P. The way to do that is to look at all the cones of influence that contain P. For every point on the current front, I look at the cones of influence and count all of and see what are the ones that contain P, and among those, take the fastest cone, the one with the smallest slope. And that slope is an upper bound on the slope of the cone of influence at P. And you can see a certain monotonicity property. If I advance P in time to P prime, P was influenced only by Q, but P prime is influenced by both Q and Q prime. Therefore, the estimated wave speed of P prime can be faster than the estimated wave speed at P. Now, this is the only assumption we make about wave speeds. So, what are the challenges in meshing when the wave speed is not constant? When the wave speed is not constant, we cannot be greedy at each step because we sort of have this logical problem. How do we maximize progress at the current step when the constraints depend on the outcome of the current step? In fact, constraints depend on what happens in the next step, which depends on what happens in the step after that, and so on. So the solution that I propose for this problem is to give an algorithm that really uses the no focusing assumption to look ahead each 10 pitching steps of the algorithm. So it's going to simulate at each step the next few iterations of the algorithm to conservatively estimate the future wave speed that it will encounter in the next few steps. And given this conservative estimate, the new algorithm can maximize the 10-pole height in the current step. Starting on slide number 26, I want to illustrate what this kind of look ahead and why it is necessary. Again, the situation front indicated the wave speed of PQR by this circular disk. The current gradient vector is at point number 0. Now, if the wave speed, again, imagine the process of advancing P is a continuous process where P goes to P prime. If I advance the gradient vector from point 0 all the way to point 1, as long as the wave speed does not increase, as if the wave speed remains constant or decreases, it is sufficient to stop at point number 1. Because we know that at point number 1, the new triangle P prime QR is still inside its disk and is causal. And in the next step, when the new local minimum Q is advanced, as indicated by the red arrow, it will make positive progress without violating causality. On slide number 27, I illustrate what happens when wave speed actually increases. In this continuous process, as the gradient vector advances from 0 towards point 1, the disk is also shrinking. So at the blue disk represents the wave speed, the reciprocal of the wave speed of triangle P prime QR. So at point number 2, the slope of triangle P prime QR equals the causal slope on P prime QR, equals 1 over the wave speed. So the algorithm better constrain the height of P prime so that the gradient vector does not reach point number 2 and does not exceed it. Otherwise, P prime QR will not be causal. So causality limits the progress at this step. But the situation is even worse, as indicated with the red arrow, because in the next step, when Q is advanced, the gradient vector immediately leaves this disk, and because of this monotonicity property, the new triangle is bound to be not causal. So on the next slide, I show a sufficient condition to guarantee that the next step is valid. What one can do is, starting from point number 0, we can constrain the progress only to point number 3. The point number 3 is computed as follows. I draw a disk corresponding to the globally maximum wave speed, which I can compute, by the way, from the initial conditions. And that is an upper bound on the wave speed at any point in space-time. So I know if I stop at step number 3, the new triangle P prime QR is going to be causal because it's inside the smallest possible disk. At the same time, by translating the progress constraints inwards and plotting them relative to the smallest possible disk, I ensure that in the next step, when the new vertex Q is advanced, it will remain causal and still make positive progress. So this is the notion that in the current step, advancing vertex P, I limit its progress so that in the next step, even if the fastest wave speed is encountered, progress is still guaranteed, and causality, of course. To do that, so this is the formal definition of the invariant which lets us do this. We want to guarantee a function that, we want to guarantee progress that's a function of the local geometry. So let delta be a function of the shape of triangle PQR. I define triangle PQR as H progressive if and only if it is causal. And depending on the value of H, an integer parameter, the following two cases occur. If H is 0, we make the worst case assumption on the progress constraint and impose a progress constraint that depends on the global maximum wave speed. If H is greater than 0, then you can see that the definition is recursive. PQR is H progressive if after pitching the current local minimum to P prime QR, the new triangle is H minus 1 progressive. And the horizon parameter H limits the number of look-ahead steps that it can make. So from this definition, you can probably easily see that there is a recursive algorithm to determine whether a given triangle is H progressive or not, as long as you have a way of estimating wave speed, a way of measuring future wave speed. There's another complication that occurs when wave speed is not constant. Basically, that a fast wave can overtake a slow wave, and therefore, when I pitch the leftmost local minimum vortex, the height of the tent pole may be constrained by a wave speed that is from a very distant point on the front. And therefore, we have non-local cone constraints, and this problem we solve by using standard data structures. So that was an outline of the algorithm to handle changing wave speeds efficiently. In addition, we also are concerned with adapting mesh resolution. So on slide number 31, I'm illustrating our refinement procedure. To adapt the size of space-time elements, we actually bisect or coarsen elements on the current front. The choice of bisection method, we choose newest vertex bisection, which is illustrated in this figure. Repeatedly bisecting a single triangle produces predictable shapes that repeat. On the bottom figure, I show what happens when we have refinement and coarsening happening, and how it fits into this advancing front framework. After a couple of tent pitching steps, in the third figure, the meshing algorithm refined a triangle of the front, and as a result, by pitching the local minimum vertex, I created a blue tetrahedron, which was smaller than if I had pitched the vertex of a larger triangle. Continuing the process, after 2 more tent pitching steps, I managed to make the 2 triangles coplanar in space-time and merge them. So I undid, I removed the previous refinement.
Hold on, sorry to interrupt. You're on slide 31.
I'm on slide 31.
You have a sequence of 6 figures in the middle with a very red, green, and blue.
Yes.
Okay, so this is what you were talking about?
Yes.
Can you just review what you were just saying there?
Yes. Step, I choose to bisect the large red triangle. And in the first step, I illustrate, in the third figure, I illustrate what happens when I pitch a vertex of the smaller triangle after bisecting the larger triangle. And that creates the blue tetrahedron, which is smaller than if I had not done the bisection. So if you want to make smaller space-time elements in the future, we make the current front triangle small. I see. And the reason the blue triangle is smaller, suppose the wave speed is fixed and is unity, is because the amount of progress is proportional to the size of the spatial size of the triangle and the wave speed. So a smaller triangle will give a smaller tetrahedron, will give a smaller tent pole than a larger triangle. And in figure number 4, one more tent pitching operation has been performed. In figure number 5, another tent pitching operation is performed, and there is, as a result of which, 2 small triangles on the front are coplanar in space-time. And in the last figure, I have merged these two triangles to get the original big triangle back and pitched a vertex of that big triangle to get an orange big tetrahedron. And as a result, you can see that the space-time mesh is not a conforming triangulation. You have one tetrahedra adjacent to two tetrahedra. The two tetrahedra cover one triangle of the bigger tetrahedron. So in figure number 3, the blue tetrahedron has an inflow triangle which covers only half the outflow triangle of the red tetrahedron underneath it. So this is what I mean. It's the space-time mesh is weakly conforming in that sense. So the thesis that defines something called the weak simplicial complex, and that's what we get as a result. So what actually triggered this bisection and allowed us to coarsen? In some sense, we don't know, but we don't care because the algorithm has to anticipate and process any number of refinement demands. But in practical cases, we want to adapt to numerical accuracy requirements. So as I point out in the caption, bisecting triangle in the current front creates smaller tetrahedra in the future, and coarsening is the opposite operation. So what this means as far as the progress constraints are concerned, we need to make sure that even after an arbitrary number of refinement steps, we still have a progressive front. And we do that by adapting the progress constraints to the shapes of the triangles generated by repeated refinement. So bisecting a single triangle repeatedly creates at most 8 different homothetic shapes. And so we impose 8 different progress constraints simultaneously. And that gives us 8 forbidden zones, which represent the progress constraints. On slide number 33, I give an example of, I go back to the example of the crack tip wave scattering problem, and I show the construction of the mesh adaptively and the solution as it was computed using this mesh. The analysis was done by Reza Abedi. The visualization is a per-pixel visualization of the solution, which was done by Yuan Shu. And I myself and Shoheng Chung were involved in the implementation of the meshing algorithm. On the left is a movie of the construction of the tetrahedral space-time mesh. This is a linear adaptive example. The problem is linear, so the wave speed is fixed depending on the material of the shape of the plate. On the right, I illustrate the solution as well as the solution superimposed with the mesh itself. So I'm going to play the movie on the left, which is the construction of the mesh.
I am able to play the movie. It just took a while to load QuickTime.
Ah, I see. Okay. So
I just click on the figure.
Excellent. So the movie is showing the incremental patch-by-patch construction of the mesh. The space domain is rectangular. That's the bottom of this volume. Time is increasing upwards. What you can see is the front, which is not flat. It's not a constant time function. And the front triangles are being refined and coarsened in response to a dissipation-based error estimate. And you can see that the front is refined near the shock fronts and other places where the solution is doing interesting things. The space-time volume itself, on the boundary, you may be able to see sort of a cross-section on the boundary. You see how the waves are propagating and reflecting off the crater. I'm going to play the movie on the top right, which illustrates the per-pixel solution. Here, this is a constant time slice that is being animated through time, starting at time t equals 0, where the initial stimulus is applied. You can see a plane wave starting at the top edge and traveling downwards, and it reflects off of the crack tip in these circular patterns. In this movie, the height field is the speed of the wave, and the color field is the strain energy density.
It's actually the velocity of the material, not the speed of the wave.
Velocity of the material. I see. Okay. So it's a normal.
Just like when you're in the ocean or the wave, your velocity is the same as the wave's velocity.
Oh, I see. Okay. So Professor Haber just corrected me on what the height field actually is. I'm going to play the movie at the bottom right, which is again a constant time slice. This constant time on the solution. And proceed to slide number 34. To combine these two last examples, the last two algorithms, the last two solutions that I talked about, that is to do mesh adaptivity in the presence of nonlinearity, I give an algorithm to adapt size and duration of elements by unifying the adaptive progress constraint, the figure with the 8 different red forbidden zones, with this algorithmic process of looking ahead at every step to anticipate future wave speeds. However, there is another improvement we can make over this simple unification. During the look ahead in the next 8 steps, if the algorithm predicts a bad quality element due to increasing wave speed, because the algorithm is simulating itself in the next 8 steps, and it anticipates that it is actually going to create a 10-pole height that is very close to the guaranteed minimum, then the algorithm can choose to preemptively refine the front. By creating smaller triangles, it is likely, depending on the wave speed function, that the algorithm actually creates elements with better quality, with better temporal aspect ratio. I'll postpone the definition of temporal aspect ratio until later, but basically, it's the ratio of the 10-pole height. It will create elements with better ratio of 10-pole heights to the spatial width of the triangle. And if the algorithm can prepare for the future refinement, now this refinement is chosen and triggered by the algorithm itself, because it is free to modify the front as it feels, then actually more progress can be made in the current step, because the progress constraint can be relaxed. And formally, this is the new invariant. On slide number 35, the new invariant is HL progressive, where H and L are 2 integer parameters. I can make the progress constraint adaptive to the progress constraint that is imposed on a descendant triangle. I can make it adaptive to the level of refinement of that triangle. And it's a recursive definition in the same way as the H progressive definition. A triangle is H progressive, HL progressive if it is H progressive, and after bisecting it, it is HL minus 1 progressive. And the base case is where we anticipate an arbitrary amount of refinement that we have chosen not to simulate. I mean, we have a bounded number of simulation steps that we impose, and that is the base case. So again, from this definition, there is an easy algorithm to determine if a triangle is HL progressive. In the thesis, I give an algorithm to maximize progress at each step, subject to this HL progressive invariant. I'm going to show next on slides 36 and 37 2 examples with simulated physics. They're not actual solutions of a physical problem, but they illustrate the behavior of the algorithm, the adaptivity of the algorithm. On slide 36, I have an example which is roughly a grid-like triangulation of a square domain in space. Time is increasing upwards. I show the space-time mesh. The mesh is adapting to two different fields which I artificially imposed over space-time. One is the wave speed. Near the bottom right, the wave speed is slow. Assume it looks like it could be unit, but I'm not sure. It is a slow wave speed at the bottom right of the figure. Then there's a fan of fast wave speeds. There's a constant, very fast wave speed, a wave speed of 4 that is in an annulus with origin at the center, and it's an expanding annulus. Inside the smaller disk of the annulus, the wave speed is again back to the slow wave speed, which is unity. However, the element size, there's another field which also dictates the adaptivity, which is the temporal aspect ratio. I chose temporal aspect ratio as a test example and required the algorithm to maintain temporal aspect ratio within a certain hysteresis zone. And this example may not be very illustrative of what's going on in the really dark zone, but you can see 2 things here, 3 things. One thing is that the duration, the heights of the 10 poles are the 10 poles are taller in the zone where the wave speed is slow at the bottom right, and also in the corner in the middle, where at point 0, 0 t, the coordinates are 0, 0, and the space coordinates are 0, 0, and the time is the maximum time. Around that zone, you can see the 10 poles are again back to being tall because the wave speed is slow. At the same time, you can see by looking at the front that the size of the triangle has adapted to this temporal aspect ratio requirement. And so there are smaller triangles inside this annulus than outside. On slide number 37, I show a second example. I start with an initial triangulation, very simple, consisting of two triangles. Going back to slide number 36, I have a similar situation that I imposed, but not quite. So I want to use slide number 36 to illustrate what the simulated physics was doing. Again, in the bottom right, there is a slow wave speed, say unit wave speed. There is a fan of smoothly increasing wave speeds coming out of the origin. There's a discontinuous jump from the slow wave speed at the bottom to where the fan begins. The wave speed in the fan goes up, and again, there's a discontinuous jump down back to the slowest wave speed above the fan. So what I show on slide number 37 is a movie, which is an animation of the front viewed orthographically from above. So it's going to be the spatial projection of the front. The mesh is adapting to the changing wave speeds. In addition, I imposed an adaptability criterion that depended on the maximum and minimum wave speeds within every tetrahedron. So remember the way adaptability works. The meshing algorithm creates a patch that is solved. If the solver decides that that patch is not acceptable because of error, then it will reject the patch, and in response, the meshing algorithm will bisect the front and create smaller elements. Here I'm simulating that situation by taking the tetrahedron, and instead of sort of solving it, I measure the fastest and slowest wave speed anywhere in that tetrahedron using this simulated wave speed function. And if this ratio exceeds, it does not lie in a certain zone, then I choose to, if it exceeds the zone, then I choose to bisect, to reject the patch and bisect the front. If it's below the zone, then I allow the algorithm to make the triangles bigger to coarse them. And as a result, what you would expect to see, and you do see, is the following movie. This is an animation of the front. You can see as the leading edge of the fan travels through the domain, the triangles are very refined because all the tetrahedra that cross this jump will have a large ratio of maximum to minimum wave speed. And that leading edge will be resolved with smaller triangles. Within the annulus, the wave speed is increasing smoothly, so there is not as much difference for the triangle size. And so in fact, some coarsening happens behind the leading shock front. Then the trailing edge of this fan, as it travels through the domain, causes similar behavior. Now the fast wave speed is on the old front and the slow wave speed is on the new front, and that causes this discontinuous jump causes the mesh to be resolved, and this process continues. I see I'm running a little low on time, so I'll speed up a little bit with your permission. On slide number 38, I summarize my main result. Given a sequential mesh, the input to our algorithm, I build a space-time mesh of the space-time domain one dimension higher with the following guarantees. The first is the finite termination guarantee. For every time t greater than equal to 0, the space-time volume across 0t is contained in the union of a finite number of simplices. The second is the non-degeneracy guarantee, that the minimum, the worst case temporal aspect ratio of any space-time element is bounded from below. I define the temporal aspect ratio of any element as any element constructed by tent pitching as the height of the tent pole to the duration of the element. So the duration is the maximum time coordinate in that element minus the minimum time coordinate of that element. So the temporal aspect ratio being bounded means that the volume of the tetrahedron is bounded from below. It's positive, and it is likely to give an accurate solution. Notice that these are worst case theoretical guarantees. Additionally, in 2 dimensions cross time, our algorithm adapts the size of space-time elements to a posteriori error estimates, provided the number of refinements is finite, or equivalently, where there is a minimum element size, our algorithm terminates with a finite mesh for every target time. There are other results that I omit from the start. The adaptivity problem, as I mentioned, is open in dimensions d greater than or equal to 3. I want to quickly go over the newer results, the newer work we have done recently. I propose new meshing algorithms, new meshing operations, such as pitching inclined temples. This corresponds to a vortex that is advancing in time as well as moving in space. Edge bisection, which is newest vertex bisection, but with a slight subtlety, which is how to choose the newest vertex of each triangle. And we can move the newest vertex around. Edge flips. In the spatial projection of the triangle, we flip an edge, which we achieve by creating a patch consisting of a single tetrahedron. Vertex deletion, which in this case, we delete a degree 4 vertex, which is a local minimum, possibly by inserting 2 tetrahedra on top. So filling the hole with 2 tetrahedra, and on the new front, that vertex is absent. So notice that we can also do vertex insertion by the opposite of this operation. Why are these new operations useful? On slide number 41, geometry and topology of the domain can change over time. For instance, you have a solid rocket fuel, and because of combustion, the shape of the residual rocket fuel is changing, and the mesh must adapt. I mean, the mesh must be a mesh of the domain that you want to solve. Therefore, the mesh must adapt by changing the size or by varying the placement of mesh features or both. In order to do that in our advancing front framework, we incorporate these operations like smoothing, which are usually in a classical sense performance or a global remeshing step at each time instant, except we do it in our local advancing front method. So here is an initial algorithm. The algorithm is basically a policy, a priority list of how to choose the different operations that are available to us. Now we have a wider menu of operations, and we just have to choose at each step which one to perform. The first operation we prefer is to coarsen the front. If the front is coarse enough, then we try to flip an edge. If it improves the spatial aspect ratio of the front, and that is likely to make the meshing algorithm more efficient, create better quality elements and fewer elements in the future. We choose to pitch an interior vertex in an inclined fashion to smooth the shape of the local triangulation. And finally, the purpose of doing the first 3 operations, or the reason the first 3 operations have higher priority, is so that we can guarantee to perform the 4th operation, which is to actually track the boundary by pitching the boundary vertex in the prescribed direction computed by the solver. We can also use additional heuristics, bisecting longest edges of triangles, smoothing out different velocities. Each operation is performed only when allowed by the solver. On slide number 44, I have an example of a movie which shows, again, a simulated physics, shows a simulated boundary motion. The figure is the initial triangulation. It's a square domain triangulated in a grid-like fashion. And the top edge of the domain is traveling downwards. Correspondingly, vertices on the left and right boundaries are also traveling downwards. The bottom edge is static. And I'm going to play the movie and show you an animation of the front, just like before. Other movies played in the computer. Interior vertices are
Top edge moving around, wobbling around quite a bit. Is that just an artifact of either pitching, or is that?
That is because the different points of the top edge are not at the same time coordinate. So some vertices have advanced further and therefore further below than others. Yes.
What's the significance of the pink or whatever at the top?
Right. So so Professor Heath's question was, what is the significance of the pink triangles that you can occasionally see at the top edge? So we are seeing here the front, but also just underneath the front are the tetrahedra whose outflow facets are on the front. And those tetrahedra are colored in pink. And when you pitch an inclined temple, you get an inclined implicit facet, an almost vertical facet. And sometimes you see those implicit facets as the pink triangles.
Those are behind the front.
Those are below the front. And
You didn't see them in the earlier one.
Right.
just moving straight.
Right.
Right.
Some of the triangles at the bottom corners in
Right.
particular seem to be getting kind of little conditioned in terms of aspect ratio.
Yes, yes. I was, for this purpose of the simulation, I was not able to implement an adaptive strategy that would fix them. Like when they start getting degenerate, do adaptivity, introduce new vertices, and smooth out that triangulation. I think I can do that now with the newer code. The other reason is also, the other problem is also that the meshing algorithm stops when those triangles get degenerate. And I think that's because of some logic that decides where to advance the front next. And since some of the code is written by other people, I'm not able to determine how to make that work the right way. But yes, they do get degenerate, essentially, they collapse. And
So that's
I
because
mean,
you need to remove vertices rather than add them.
yes, in this case, I did not allow the boundary vertices to be deleted, but it could be.
Well, it may be that degeneracy at the end of the simulation is unavoidable if those vertices are actually reaching the target time where the top edge touches the bottom edge. Then there's no way around the fact that you're going to get degeneracy eventually.
Well,
That doesn't quite happen here.
if you keep adding vertices, you may get a very refined mesh, but you should, if you are able to add vertices, you should be able to keep good aspect ratio.
Shripad, I finally got getting the movie up here. It takes a long time to load. This is a movie from page 44.
Yes.
Okay, I'm going to play it here. It's not that long. So what is it I'm looking at here?
So this is an animation of the front. I initially start with the square domain, and the square is collapsing downwards. So this, I mean, the newer implementation does have more interesting things it does. It manages to do.
We should probably finish up this.
Excellent timing. So to conclude, I would like to summarize my results. I give an algorithm that adapts mesh resolution to a posteriori numerical estimates. This is necessary for efficiency and tractability of the solution. I give an algorithm to adapt to changing wave speeds, which was not possible with earlier algorithms. And the algorithm performs both adaptation operations in space-time, and these operations fit in a framework for smoothing to improve mesh quality and are useful for tracking moving boundaries and other singular surfaces in space-time. To just view the impact at a glance, on slide number 49, I show a matrix of the problems that we have considered so far. The non-adaptive linear case is when the triangulation is fixed, and so basically the sizes of the tetrahedra are dictated by the spatial size of the underlying triangulation, and this does not change. And linear means that the wave speed is constant. So this was the 10-feature algorithm, which worked in arbitrary dimensions, but was constrained to solve only non-adaptive linear problems. In this thesis, I present an algorithm to solve the problem at the bottom right, which is to solve nonlinear problems adaptively. To get to that, I had to fill the matrix. So I first, we had a paper and sausage on how to do adaptivity, assuming a fixed wave speed or non-increasing wave speed. Then I had a paper at the meshing round table, which was on adapting to changing wave speeds. And then a paper at EuroCG, which is the journal version is currently in submission, which is the unified version with the HL progressive invariants to solve nonlinear problems adaptively. In all of these cases, we have theoretical guarantees. We efficiently create solvable meshes. Smoothing and boundary tracking, that is these new operations, represents recent work which do not create inverted elements, so we can guarantee that we won't create sort of elements with negative volume. However, this is done only by sort of assuming a worst case quality, spatial quality of the triangulation of the front. So if the front triangles degrade in spatial quality more than expected, then the algorithm can and does get stuck. Some future directions, I think there are lots of interesting open problems. I'll list 3 of them. As I said, adaptivity in 3D cross-time and higher remains an open problem. It would be very interesting to give a provably correct and complete boundary tracking algorithm for interesting classes of motion. And a of course, domains do also change topology. They may split up into multiple components or create voids and tunnels, and it would be challenging, very challenging, to process these changes and create a space-time mesh for that problem. So thank you for your attention. Any questions?
So we should take questions from the audience at large first.
Bound the time to solve a single patch and the number of patches in the mesh. So the time, by order n, I mean that the time to solve a single patch is a constant. It depends on the degree of the underlying space mesh. So if you pitch a vertex of degree k, you create k tetrahedra in the patch. So that constant will appear there. But then the sum is just the number of patches. So this will be a constant times number of elements. If each patch consists of a constant number of tetrahedra of synthesis.
Would it perhaps be better to say that the time to solve a patch, assuming that the degree of the patch, meaning the number of elements in the patch, is bounded, the time to solve the patch is bounded rather than to say it's constant?
I agree, right? It would be bounded, but I guess it would depend on the following: the degree, the basis function, and the computation time. Which I can.
But right, so you need to make some assumptions about the maximum number of elements of the patch, about polynomial order, maximum polynomial order, etc. Then you can say that there's a constant that bounds the time. And the solution time will be better than that, any times that time.
I see.
Better than equal to.
Any other questions?
What do you expect about the 3D cross within the adaptive?
So Damon's question is what I expect about adaptivity in 3D cross time. There are extensions of US vertex bisection to arbitrary dimensions. So it is known how to repeatedly bisect a mesh to create smaller simplices. However, to incorporate that into our advancing front framework, we need new progress constraints in 3D cross time. And right now, it's not clear what those progress constraints should be. And there's also, the goal has also been to give sort of sufficient constraints, but also progress constraints that are as weak as possible, because we anticipate that in practice we could make the progress constraint weak and actually get much better results. And just like in 2D cross time, the constraints are required. And there are two samples, so they're pretty narrow. Professor Louis, do you have any questions?
I'm just slide 31 here. I still find this issue a little confusing here.
Okay.
Because you're having refinement and parsing, and I understand the basic operation, vertex bisection and portioning, of course, is the opposite here.
Right.
And what you say is that because of these operations, you get only a weak spatial complex.
Yes.
Can you explain how that's different from a standard differential complex, which I do understand?
Yes.
And then, so how does the weak one differ from the standard differential complex? And then, how does this affect the difficulty, the overall numerical solutions? I mean, underlying the mesh is just to support the discontinuous Galerkin method. So, how does having a weak differential complex affect the rest of the computation for the continuous Galerkin?
Right. So a simplicial complex, in this case in 3D, because it's a tetrahedral mesh,
Right.
would consist of tetrahedra such that adjacent tetrahedra share or whereas a weak simplicial complex is a simplicial complex where in this case adjacent tetrahedra share a triangle that is the entire facet of one of the two tetrahedra, not necessarily both.
Oh, I see. So, for example, in the third figure from the left, the red and blue here,
Right.
the bottom facet of the blue tetrahedron is only part of the face of the red tetrahedron.
Right, but it doesn't allow arbitrary intersections. The intersection is the entire facet of the blue tetrahedron.
Right. I see that. Okay, so that is a weak simplistic complex.
Yes.
And then how does it affect the numerical solution?
The numerical solver, the SDG solver, is quite comfortable with patches that look like this. The requirement to have a weak simplicial complex is for convenience. For instance, because the two tetrahedra have a reasonably nice intersection, that common facet, which is the entire facet of the blue tetrahedron, automatically has a nice parametrization which facilitates integration along the common boundary.
I see.
But it is for convenience, because it is continuous formulation, the SDG method is in fact able to solve essentially any causal partition of spacetime. So this is I think I would say a positive aspect of the meshing algorithm, because even with this restriction of having weak conformity, the algorithm is still able to do mesh activity.
Okay, thank you. That's really the only main conceptual technical question I have. Thank you.
Any other questions from the committee while the audience is here? So I have one. Can you say briefly, what do you think the outstanding technical issues are in getting up to the point where you can actually say, simulate forming rocket fuel, do a real physical simulation involving moving vectors?
So Jeff's question is, what are the technical difficulties before we can say that we can simulate burning rocket fuel, for example?
Just some real physical problem involving boundary motion. Let's say 2D cross time.
In 2D cross, thank you. Maybe I should consider the 1D cross time example first. So a 1D domain is just a real interval, a bounded real interval that has been subdivided, and the boundary is just two vertices. So we still want to restrict ourselves to this advancing front idea. The only boundary motion is that the vertices are moving either to the left or either to the right, and elements may get degenerate because some segment on the front may collapse. There I think we are in good shape because we are able to, assuming that the speed of the boundary motion is bounded, which I think is a reasonable assumption, we have, and it's less than the causal slope, for instance, or we can decrease the causal slope. We have some way of anticipating discrete events at which combinatorial changes occur on the front. So when does an edge of the front collapse? And given that we know, we can predict when this event happens, we can account for it in a manner similar to the look-ahead algorithm, and slow down the algorithm, slow down the pitching, so by the time this discrete event happens, we are in a situation where we can coarsen the front and completely eliminate the edge. The segment is about to collapse. In 2D cross time, we need to do something similar. We need to have an estimate of when a discrete change will happen. When will a triangle become degenerate? The problem there, I think, is similar to the fact that we needed progress constraints to anticipate when a triangle would no longer be causal, or if we had an estimate of when a triangle would no longer be causal, we could slow down the algorithm by imposing progress constraints so that we could help this situation. And I think it may, the main challenge is to guarantee that, well, first that you can predict when discrete changes in the combinatorics of the front happen. That's reasonably easy to do. And secondly, to ensure that the operations that can be used to prevent this collapsing to happen can be performed well in advance of this event. And I think the main challenge is possibly coming up with additional slope constraints on the front to ensure that, for instance, an edge can be flipped, that a vertex can be deleted, that a new vertex can be inserted to the opposite vertex position, and so on. I've seen some papers where they talk about arbitrary affine motions of the boundary and how do you track that, but by moving the interior vertices. But the algorithm seems so complicated because essentially it's solving PDEs of its own to model this motion. And so I think to do it simply is very challenging. Does that answer your question?
You know, I was hoping to hear something about what motion is to begin with.
Oh, yes.
And how is the motion actually specified?
So I think in the abstract, I'm thinking of some sort of implicit representation of a surface in spacetime, which either represents a moving boundary and a way of querying this implicit surface to detect when a endpoint, for instance, crosses the surface. Am I just below it, or am I just past it? And I think that may be sufficient. Compute this is like similar to the cones of influence. We have ray shooting and we say, okay, at this point, I'm going to intersect the fast rays. As long as we can answer queries of that sort, I think that may be fairly general description of moving boundaries. Again, in theory, I don't know how implementation will be seen. So right now we are sort of describing motion by moving the boundary mesh, or the boundary of the mesh. And that may be adequate, but maybe topology
Follow on to that, another question. So this relates to what you were just discussing in your earlier comment that the adaptive moving boundary algorithm can get stuck if elements get too degenerate, their quality gets reduced. So to me that suggests that you ought to be thinking about optimizing element quality or maintaining a minimum element quality rather than thinking about sort of catastrophic events when you get a degenerate element. You want to stay well away from that. So what are the prospects for, along the lines of what you were just discussing, maintaining the capability to do the basic operations like edge bisections? One that seems to come to mind as a remedy for bad elements or vertex insertion and things of this sort. Edge flips, all of these operations, make sure that they're always available by sort of extending the progress constraint. But then using those operations to maintain some minimum element quality, provable, ideally minimum element quality, heuristically if not provable.
So I feel right now the level of research is at the same stage as for the temperature algorithm before progress constraints. They sort of make this worst case assumption, and as long as you are far enough away from the worst case assumption, in this case, say the smallest angle or the largest angle in the mesh, you are, at least in practice, likely to be okay, and the front is likely to advance. And what I don't know how to do is how to stay far enough away from this catastrophic situation. And I sort of have this similar problem, like with the increasing wave speeds, is, oh, the catastrophic problem is going to happen here. I need to sort of have my distance to the degenerate situation in the next step. But I can't sort of repeatedly do this unless I'm guaranteed at some point to finally completely resolve the degeneracy. And I don't know how to do that. It may be that we may need maybe like even more different operations that can be guaranteed. Even though we have sort of a basic vocabulary that allows us, at least in the space mesh, to take any triangulation or any other triangulation with the same vertex set. The reason for having a more complicated vocabulary is because it may be easier to achieve this in space-time, while staying with our restrictions of weakly conforming and bounding the temporal aspiration and so on. So I don't know the answer. It may be a good thing to explore the simple classes of motion for which the current algorithm does work, and that will help us identify what are the situations where it doesn't work, and see if we can devise constraints to avoid those situations. Again, I'm thinking similar to the requirement for progress constraints.
Just one comment on that. That may also require that we make stronger assumptions about what the boundary motion looks like. For example, we may need to impose a Lipschitz condition on how quickly the boundary motion changes, or make some stronger assumptions about what the physics is going to tell us as far as boundary motion is concerned. Maybe we get acceleration as well as velocity or something along those lines. But right now, things are still very preliminary.
The other question I had was kind of in the same vein as Professor Louis' question about how this all hooks up with the numerics. And I didn't hear you say anything that, say, contrasts this approach to an adaptive transient algorithm, transient being a time-dependent problem, versus other available methods, such as, let's say you're doing ALE, arbitrary Lagrange univariate moving mesh method, with a semi-discrete approach with time stepping, and there have been such algorithms done with activity. I'm thinking actually there's at least one key advantage here, but I didn't hear you discuss this point at all.
Maybe I'm not aware of the advantage. I'm glad it's there, but I'm not sure I can stay organized.
So we should fix that problem before you graduate.
Seems to me that, just as a comment on this question, that dealing with boundary motion should be easier in space-time than it is in the separate
Remeshing global rehash.
Yeah, I mean, in the conventional approach, you don't really, it's kind of hard to say what I mean, but you simply have time marching on, and so you have to deal with dynamic change, as it occurs. You can try to anticipate it, but you don't have any sort of bridge to it the way you do with where you think of your non-trivially meshing. So I think there's hope that it actually could work better and that could actually become one of the advantages of space-time meshing. So it has a better handle on how to deal with boundary motion.
See, with the exception of refinement, all of your adaptive operations are executed through space-time elements rather than instantaneous refinement or coarsening of the front. And particularly coarsening operations would require a projection of the old solution written on the old mesh, on the old front in effect, onto a new mesh, which is the new front. And that's an intrinsic source of numerical error that can't be done perfectly. Whereas here, there is no such projection because the topological connectivity transformation of the front happens during a space-time element or a space-time patch. It's all built into the method. There are no such projections, so there are no projection errors in the activity here. The only exception, of course, is not to error, but to the fact that you're not doing the space-time operation of refinement. But that, because it's a weak simplex, actually that's another reason for using the weak simplicial complex, is that because there's nesting of the refined mesh and the old mesh, you can exactly, the projection to the new mesh is exact. So there's no error there either. So zero projection error is a bullet item.
Other question? So, if there are no more questions from the audience, oh wait, there is a question. Oh, sorry.
So the speaking,
No, edge flips are, we know sufficient conditions under which edge flips can be performed. Basically, this progressive invariant, but I mean, there's sort of some initial ideas on how to do that, how to always guarantee, if you know that you want to flip this edge, guarantee that it will actually be flipped eventually. But I can't think.
so it was very easy ground example, so that's pretty.
Yes, it would basically involve looking at larger neighborhoods, second degree neighborhoods, and saying, okay, I want to look at my second degree neighborhood and impose some sort of slope constraint on this, like the neighborhood of the vertex, not just a star, but the second order neighborhood, and imposing constraints on that neighborhood to eventually guarantee that something will be flipped.
So let's try this again. Let's make Shripad again.